convenient. In this way, the annotation cost is significantly reduced. Most weakly supervised learning methods can be viewed as a multiple instance learning framework. The MIL framework denotes an image with thousands of proposals as an active instance. However, the loss function of MIL is known to be non-convex. During the training procedure, MIL tries to find the most confidence instance to classify the instance back. It will be falsely localize the object path caused by the non-convex problem. There are many ways to solve the non-convex problem, such as the regularizations and smoothing. In this work, we introduced the continuation methods to deal with the non-convex problem. The continuation methods optimize the non-convex loss function. Firstly, approximate it to a non-convex function and find an initial solution. And then the convex function is changed to be less smoother based on the initial solution. With the loss function gradually anneal to the original non-convex function, we can find better solutions. Before introducing the continuation MIL, we first revisited MIL framework. The MIL can be concluded as two alternative steps: instance selection and detector estimation. In the instance selection step, the algorithm selects the most confidence instance to classify the instance back. However, when the back label yi equals to 1, this term is non-convex and thus cause local minimum. We then introduce the continuation methods to solve this problem. The continuation MIL is to convert the non-convex loss function to a series of smoothed loss functions, starting with a convex loss function. This is done by the introduction of the continuation instance subset. The continuation instance subset is controlled by the continuation parameter lambda. When lambda equals to 0, the instance subset contains all the instances in the bag. And in this situation, the loss function turns to be convex. When lambda increases to 1, each instance subset contains only one instance, and the loss function of CMI will be equivalent to that of the MIL. The loss function of CML is then defined on the instance subset. During training, the method select the most confidence instance subset and estimate detector using the graduate equivalent positive and negative instance. In network implementation, we adopt a multiple branch framework. We can also use multiple detector estimation branches as in OICR. In experiments, we first studied the effect of the continuation parameter lambda, and log function achieves the best performance, which indicates the smooth procedure should be used in the early stage. We also evaluate the performance evolution on training set, and it shows although image classification converges slower, the object localization finally significantly outperforms the baseline. We find a phenomenon that during the continuation multiple instance learning, the activation area of some images gradually reduced and converges to the object area, which forms the stable semantic extremal region. The emerge of SSER indicates the CML continuously suppress the background while activation object region during training. The experimental results on VOC datasets has shown CML outperforms the state of arts, and here are some detection results of CML. You can come to our poster for more details, and our post ID is number 24. Thank you.
전체 여기가 많은 중국하고 인도 둘 중에 하나인 것 같아요.
Good afternoon, I'm Chiuna. I'm Chiuna. I'm to introduce our paper with supervised learning of instance segmentation with interpixel relations. Instance segmentation was the major task of the division. We want to detect its object and find its class and mass individually. Thanks to learning, instance segmentation is achieving great success in this area. Through instance segmentation, we typically use fully supervised learning. The problem is, supervised learning needs at least thousands of segmentation masks for training. So we thought that what it could just automatically generate training data using image classifiers. Image level labels are just simple keywords like sheep or cat, which tells us that what kinds of objects are in an image. The problem is they do not provide any information about shapes or location of objects. But luckily, some add-ons show that you can find some object paths, if only from the image level class label using an image classification network. This technique is called class equation mapping. Still, this is just a sparse and blurry attention. But we have noticed that this class of tensions are quite accurate in high score areas, and perhaps we can learn something from these areas. Specifically, you can divide camps like this. From these regions, you can partially find out where an object is and which pixel has the same class label to which pixel. Using this, you can derive two types of interpixel relations. One is displacements, and the other is class boundaries. So first, what is displacement? We are talking about displacement to instance centroid coordinates. Suppose that there is a centroid for each instance. An instance only has one unique centroid, and all pixels of the same instance share its centroid coordinates. For each pixel, we have a displacement vector, which we can add to the coordinates of the pixel, and we can obtain the coordinate of the centroid. Like this way, we can train all pixels of the same object class to have the same centroid. And please remind that each instance has only one unique centroid. So, by grouping all pixels heading to the same centroid coordinates, we can distinguish different instances, even if they are close to each other. In this way, we roughly find out instances, but we still have to find their shapes. One effective solution to this is to utilize boundaries, so that the seeds can be propagated within the boundaries and find their shapes. Of course, boundaries provision is not available in our setting. So we have also developed a way to learn boundaries without any boundaries provision. We use classification maps. On the camps, we assume that if two neural pixels belong to different classes, then there must be a boundary pixel between them. We're just not sure where the tree is. So we encourage a boundary to appear on the straight line that connects the two pixels. And in the other way around, between the same class, there should be no boundary, so we penalize boundary scores between them. So we propose interpixel relation network. This network is learned from the two types of interpixel relations. It joins to estimate displacement field and class boundary map. And finally, we can train Miles-Kahn CNN with the suitable labels. A method to distinguish different instances and also find their relationships.
Right.
And consequently, we are able to perform PRM, which is the previous best in the same setting, by a large margin, setting a new state of the art. Thanks for your attention. For details, please come to the poster and